Good morning. I'm Chris Scolese, Director of the Goddard Space Flight Center. Welcome to the center. I'm standing in Building 29, and behind me is the clean room where we're building the James Webb Space Telescope. It's the largest clean room of its kind that we're aware of. And as you can see behind me are the 18 mirrors that form the telescope. It'll be the largest telescope that we're going to launch into space. Behind that telescope are the instruments. And today what we're doing is celebrating the fact that we have achieved the completion of the integration of the telescope, and now we're beginning the phase of doing extensive testing to verify that everything is working and ready for launch. Today I'm pleased to have everybody here, and I want to introduce some of our guests from NASA headquarters. We have the new AA, Dr. Thomas Zabrukin, and we have Dr. Eric Smith, who is the program director for the James Webb Space Telescope, and Bill Oakes from Goddard is the program manager for the whole James Webb mission, who will be here today, and they'll be available later on to answer questions. Also, I'm pleased to have the administrator, Charlie Bolden, here today, who will be speaking in just a few minutes, and Dr. John Mather, who is our senior astrophysics scientist here and our senior project scientist for the James Webb Space Telescope. Now, so that you can start hearing about the telescope, I want to introduce John Mather. So John has been at Goddard for a long time. He is our only and first Nobel Prize winner. He's been with the James Webb Space Telescope almost since its inception, and certainly has all of the information about what the James Webb can do and will do when it ultimately gets into orbit. John?
Thank you, Chris. Well, welcome to our science party here today. I think it's a wonderful day to celebrate, and I want to tell you a little bit about what we're doing it for. By the way, Charlie, thank you for your advocacy on our behalf. This project has taken many administrators to complete. We've been doing this now for over 20 years, and we're almost done. So only two more years to launch. So today we're celebrating the fact that our telescope is finished, and we're about to prove that it works. So that's a pretty important milestone for today. And just as a reminder, this is not a science project. This is mostly an engineering project. There are far more engineers and technicians than there are scientists involved with this, and engineers and managers and technicians are the ones who will make this possible for scientists to discover things. So we've done 2 decades of innovation and hard work, and this is the result. We are opening up a whole new territory of astronomy. So we will see things that we've never been able to see before, because this telescope is much more powerful than even the great Hubble telescope. So what makes it more powerful? Number one, it's gigantic. You can see this beautiful gold telescope is 7 times the collecting area of the Hubble telescope. So that's the beginning. The second thing is it's designed to collect infrared light. So infrared is something that you cannot really see with your eyes. The Hubble telescope can see a little bit of it, but it's not cold. So the Hubble telescope glows and emits infrared light itself, so you cannot use it to do all of the things that astronomers have identified as their next top priority. So this telescope is going to be in outer space. It's going to be cooled to a very low temperature of 45 degrees above absolute zero, really chilly, so that it does not glow. So it's going to be very perfect as well. This mirror that you see, if you made it stretched it out to be the size of the entire United States, the hills and valleys on that mirror would be a few inches high. It's an astonishing engineering accomplishment. It is too big to go into the rocket, so it'll be folded up. And there's another astonishing engineering accomplishment there. So let's see, also to give you some perspective about what we can do with it, if you were a bumblebee hovering out at the distance of the moon, we would be able to see you, both by your reflected sunlight and by the thermal radiation, the heat that you emit. So how can we do that? We have brilliant engineering. We also have the most astonishingly good detectors that have ever been made for picking up this infrared light. So I don't want to exaggerate, but that's beyond a miracle as far as my perspective is concerned. So so that's basically how we do it. The way that the telescope works, light comes from the sky, bounces off that big mirror. It's concave, and it will be focused down towards a little point. But before it gets there, it will be intercepted by the little round mirror, which currently is folded up above the telescope. It's called a secondary mirror. It's about that big. And it will magnify the image and send it back into the instrument package, which is in this, well, it's behind that black snout there. And there was a little hole in there which lets the light in. And in the back are the instruments that will take the incoming light and convert it into digits to send back to Earth. So that's like the sensors in your cell phone camera, only way, way, way better. And they pick up wavelengths that we cannot see with your cell phone camera or with your eye. So the wavelengths we pick up begin at 0.6 microns wavelength, which is sort of reddish, and you'd be able to see it, but they go out to 28 microns, which is much, much longer, and you couldn't see it, but if it were really bright, you could feel the heat of it. So this is why we're opening up a new territory of science. You cannot do this experiment on the ground because the atmosphere glows and is opaque. The telescope on the ground would glow as well. So you just can't do it any way else besides going into space. So you see this very complex thing and you say, wasn't that pretty complicated? The answer is we have to have it to do the science that we're after. So let me say a little bit about the science that we are after. We would like to know basically how did we get here from the Big Bang. So what happened after the Big Bang? The first stars and galaxies happened some way. We have lots of predictions. We have supercomputer simulations. We can even show you a movie how it might have happened, but we don't know. You have to go look. Nature has this way of defeating our imagination. And so astronomy has always been an observational science, and you just cannot depend on your imagination alone. So what happened after that? Well, the galaxies grew. The Milky Way, which we live in as 100 billion stars, probably was formed by thousands of little bits being pulled together by gravity over billions of years. So the Milky Way that we live in today is very different from what it was when it was young. Did not all form at once, probably. Got to find out. How did the planets and the stars get formed? Well, right now we're just beginning to see planets growing around other stars. So the Webb telescope will be pointed at places where stars and planets are being born today. There's several of them being born every year in the Milky Way. So some of them are good targets for us, and we hope to see the details. Closer to home, we hope to see what about those little planets out there. The solar system, we've got lots of planets, some dwarf planets, and we will look at everything from Mars outwards. Everything is in view for our telescope. Around other stars, we'll be looking for planets around them. So sometimes they go in front of the star and they make the star blink, and you can say, I know something happened. This telescope is big enough to analyze the light that went through the planetary atmosphere and say, what are the chemicals in the atmosphere of another planet? Isn't that spectacular? So we will be able to tell you a little bit about whether those little planets out there are like Earth. There are a catalog already of things to look at. And we have a mission going up called TESS, which is going to give us a bigger catalog of better targets. So coming soon, we'll be able to tell you a lot more. We recently heard that there's a planet around Proxima Centauri, which is like the nearest star to us that we know of. And we think we should be able to pick up some information from that planet, even that one, even though it's a little tiny guy, about the size of Earth. So how did this all come to be? Well, many years ago, 21 years ago, a committee was formed to say, what are we going to do next after the Hubble? And they wrote a book called HST and Beyond, and it's very poetic. If you really want to know how did we get started, read that little book, because it still gives me goosebumps to think about what's in that book. And we're doing what they said. They said, build us a telescope, and they also said, build us the technology to study those planets around other stars, and we're doing that too. So what does it take to put this together in space? Well, it takes an international partnership. I got to remind everyone that this is a partnership that NASA is leading. And we here at Goddard are leading the NASA part of it, but we've involved many contractors around the country, including Northrop Grumman and Ball Aerospace, and what used to be Eastman Kodak is now Harris, I think. And we have detectors, the magic detectors come from our country. We've invented some stuff right here at Goddard that never existed before. And our international partners have produced, in Canada and Europe, they've produced 2.5 of the 4 instruments, and our European partners are buying the rocket that's going to take us into space. So in a couple more years, we should be at the launch site in French Guiana and ready to push the button, and maybe by this day of that month, it will already be up. Wish us luck. We have many hard things to do in front of us. We are about to subject this beautiful beast, which is finished, to see if it will survive launch. And we expect it to, but we still have to prove it. After we do that here, then we'll ship it to Texas to put it in the big vacuum tank there. we will put it in there and make it focus as it will be in flight. When it's done there, it goes to California to meet up with the warm part of the observatory where the rocket jets and the fuel tanks and the computers and the power supplies and all that are located. And it'll be there, and in particular, it'll meet up with the sun shield, which is the part that unfolds in space and protects the telescope. Sun shield is as big as a tennis court, as you know. So just try to imagine Roger Federer and Rafa running back and forth on their halves of our telescope. Just picture that and just imagine how large this is and what a hard job that is. But it's finished. We know how to do that. Just I want to check and see if there's one more thing that I'm supposed to tell you. I think that covers the most of it. Just to say, we're doing this by plan and intention. It's taken the support of NASA and the entire world 20 years to get here, and we're almost done. People used to laugh at me that said that could never happen, and it's happened. Thank you. So, Chris?
Yep. Thank you, John. So as John said, you know, this is a great accomplishment. We're approaching the completion of the whole mission, and certainly we're starting the testing of the integrated telescope right now. And as John said, it's taken, you know, our cooperation and the support of a lot of people in order to, and a lot of organizations in order to make this work, not only in the U.S. but around the world. And to all of them, we say thank you for getting us this far and helping us to ultimately develop a fantastic observatory. Now there's another person who's helped us get here, and as John mentioned, you know, it started in some ways with the Hubble Space Telescope. It has been a great success, and one of the people who deployed it happens to be our administrator, Charlie Bolden. Since his time deploying the Hubble Space Telescope, he came back to NASA as our administrator, and he has made James Webb Space Telescope one of the priorities of the agency, which has given us not only the technical stability that all missions need and the team focuses on, but also the financial and the programmatic stability to allow us to operate and develop the spacecraft and the telescope and the instruments. So with that, Charlie, I want to thank you for all of your leadership and welcome you to say some words.
Thanks very much.
Charlie?
Thank you. Let me first of all thank everybody for coming out this morning. I know some of you are here because your boss told you to come and bring your camera and your mic and all that other stuff, but there are some others of you who are here just because you're genuinely interested, and we really appreciate that. I'll let you in on a secret. Eric Smith is here, who's the program manager right now, and Eric and I work out in the mornings in the fitness center at NASA headquarters. And I said, Eric, can you give me a time that would be nice for me to go out and look at the telescope, before it gets shipped, when it's all assembled and everything? And Eric said, oh, we can make that happen. And the next thing we knew, we had this big event. So it was reminiscent of my days as an active duty Marine when the general said, okay, we want to go and have a formation, and we want to do it at 0800 in the morning, and at 0600 the troops are all out in formation. So they'll be there when the general comes at 0800. So unfortunately, I have not gotten away from some of that. I thought I would, first of all, thank John and his team, because as John and Chris have said, this was a long time in coming. And a long time in coming because it is so complex. I'm not sure how many people understand the tremendous complexity of this particular observatory, if you will. Not only from a technical and scientific standpoint, but just from a management standpoint. It is an incredibly difficult project to manage. And I want to commend the team that has been in place, that has made this happen, particularly the work that's been done over the last 6 years. Some of you who have followed JWST know that it almost didn't happen. And it's mainly because of the people that are sitting here able to talk to you today that we're all here and within 2 years of launch. I thought I would also just tell you real quickly, because I'm not sure how many people know who James Webb was. Probably a lot of people think James Webb was probably some great astronomer, who either designed and built a telescope or won a Nobel Prize or something. James Webb was not. James Webb was somebody sort of like me, only much better. James Webb was a Marine. He was a Marine pilot who served in World War II. He actually served twice. Got his wings in 1936 and served for a couple of years in the Marine Corps, and then got out, went back to school, went to GW, not very far from here, and eventually got a law degree. So he became an attorney. Did some time with pretty big businesses, and then the war broke out, and in 1944 decided he was going to go back into the Marine Corps and served, as most people did. You served until the war was over. So that's what James Webb did. You know, you say, what did Daddy do in the war? James Webb went to the war. And he came back and did a number of things in and out of government, and he was finally assigned to be the second administrator of NASA after its formation. A thing about James Webb, other than the fact that he oversaw our journey to the moon in the Apollo program and presided over the survival of the agency, actually, after the Apollo 1 fire, was his infamous arguments. And they were not discussions, they were arguments with the President of the United States on NASA's future. And James Webb, if you go to the Kennedy Library or go online, as a matter of fact, you can actually listen to the debate between James Webb, the administrator of NASA, and John Kennedy, the President of the United States, about where the U.S. needed to go next if we were going to beat the Soviet Union, as a matter of fact. And James Webb said science is the future. That would be his legacy to this agency, the fact that quietly he was one of the strongest advocates for science. And so as a result of that particular trait and the fact that he had been a previous NASA administrator, he was chosen by one of my predecessors to actually be the namesake for this incredible instrument that we have today. Just a piece of trivia. John has already talked about our incredible international team. This is a collaboration among the European Space Agency, the Canadian Space Agency, industry, academia. I could just give you numbers and names of organizations, but I don't want to bore you with that. What is important is that it shows you what is required to do something of this complexity and this magnitude. It takes teamwork. And that's what you're seeing in front of you today. We're all proud to be a part of this. We're exceptionally proud to be sort of the caretakers or the overseers of it here at Goddard, because if you look, I like to tell people, if you look at per meter or per centimeter, Goddard probably has more scientists and engineers than any of our other NASA centers. And many people don't remember that or don't even know that. So it's quite an appropriate place for us to be today to have an opportunity for all of you to look at this telescope. I think the only thing I would tell you in closing is, again, to emphasize the incredible teamwork that was required to get us here today. John, I cannot thank you enough for the leadership that you, Nick and Chris and others have exhibited over the period of time. We've got some of our contractor partners here. We all played a role in our own special way, but somebody's got to be there saying, do this, do that. And so I do want to highlight the three of you and Bill Oakes for the special work that you all have done in being the ones that said, okay, today we're going to do this. I would say thanks again to all of you for coming out for this milestone, and now we need to get on with it, get through this ceremony, and move to the next milestone that takes us to a 2018 launch. Thanks for coming out again.
Thank you, Administrator Bolden, Dr. Mather, Chris Scolese, for having us here for this great opportunity to see the telescope before it goes into space, as it will be when it's 1 million miles away and unlocking the secrets of the solar system and beyond. We will be taking some questions from reporters here in the room and from those of us following online on social media. Of course, you can always find more detailed information, images, videos, everything online at www.nasa.gov/web, W-E-B-B. And for reporters in the room, please raise your hand, wait for a microphone, identify yourself and your organization, and Keep it to one question so your colleagues have the opportunity to ask questions as well. If you're following us online, you can use the hashtag AskNASA in your post so that we can find your question and ask you. Thank you. We'll now take some questions. Look for the microphones. All right, question over here.
Hi, I'm Holly Fry from How Stuff Works. You had, is it working? Okay. You had mentioned that now what you do is you prove that this is going to survive the launch. What sort of testing is going on to do that?
Okay, so number one, we have to shake it, as it will be shaken by the rocket. Number two, we have to put loud noises on it, as it will feel the loud noises of launch, 150 decibels of something. You know, you don't want to be there yourself. So that's the first test we have to do here to make sure it survives. From here, we go down to Texas and prove that it focuses as well. That was the number one challenge. How do you make sure that you know it'll focus in space, especially after we learned that the Hubble was not quite in focus when we launched. So we learned how to do that. So that's the next step.
Next question here.
Yeah.
Oh, it's right behind you.
Oh, thank you. Thank you for this event. Greg Redfern, WTOP. For Dr. Mather, what is your most exciting observation is going to happen? And thank you.
If I really knew, I'd tell you. I'm hoping that we will find something that nobody knows is out there. So some little thing that happened in the early universe that came before the galaxies, some way that the black holes were formed. We don't know where they came from. So that's a wide open topic for scientists. And close to home, everything we know about planets out there has been a complete surprise. So I'm expecting some more complete surprises about planets. Those are the two things where I know we should get a surprise, and I don't know what the others will be.
Okay, the gentleman right next to him.
Unlike the Hubble, we can't send Mr. Bolden or any other astronaut to fix it. Can you tell us about maybe the pressure or the importance of getting it right on the ground and how you're dealing with that? Because just realizing that once this thing is out there, there's no way to fix it.
I'll let John give you the details, but it's critically important to get it right here on the ground, and that's the purpose for the tests that we're doing here, and most importantly, the tests when we get it down to Johnson in Chamber A, in the big vacuum chamber, to make sure that it can, in fact, be focused, so that we don't find, as we did with Hubble, that we don't have the ability to do what we thought it was going to be able to do. The fact that it's a segmented mirror that has individual actuators behind each segment means that, you know, we can tune it, if you will. So we have the opportunity to do what it took astronauts with Hubble to go up and put corrective lenses on it. We actually can do that. I've gotten a little education from John this morning, so the team here will actually be able to individually tune the mirror segments, so that's what's critically important. I think the only other thing, and again, going with what I learned this morning, this may be the last telescope that we build that is not modular, such that it has a capability to be serviced on orbit. You know, John can explain to you why we really don't want to mess with this one. The fact that it is a really cold telescope, and the big thing is the solar panels to protect it, and the fact that it's got sharp edges, and astronauts generally don't like being around sharp edges. So a number of reasons that we decided we weren't going to try to service it.
Yeah, I think Charlie's covered the main points, but just to assure you, our lessons learned from the Hubble were, if you really care about something, you got to measure it at least twice. And if you don't get the same answer, you better figure out why. So that was a really important lesson. We built our entire program around that.
Next question is over here.
David Kramer, Physics Today. How confident are you that this project is on track, on budget and on track?
Very confident. I will say that, and I talked about the critical importance of the technical and scientific side, but also there's the management side, and the reason I single is not the right word, but when you point to Bill Oakes and you point to Eric and Chris and John, is we made a commitment to the President and the Congress, namely Senator Barbara Mikulski, about 6 years ago, when we found out that we were not going to be able to bring James Webb into life on the schedule that we had and the cost that we had. And so we had outside experts get together with us. We took a look, and we came up with a revised schedule and a timeline and cost schedule for James Webb. We, as Chris said, it's my responsibility. That was the responsibility I took. I made it an agency priority. We look at it I look at it every month. They look at it every day. But we're on schedule, on cost, and in fact, I won't talk about anything else, but just suffice it to say we're on schedule and on cost.
Okay, great. Another question up here.
David Smith of The Guardian, just following on from that last point, is everything about this completely safe and ring-fenced, irrespective of what happens in the election next week? You know, whoever is
Hey, is it David?
Yes.
Let me tell you, and I will be the one to go out on a limb here, and it's important. We're about to go through a period of what we call the transition. We think we have an incredibly good story to tell. James Webb has stood the test of time. We spent a tremendous amount of money up front. People talk about the need for technology development. Most of the money on James Webb was spent up front before we put anything together, because this is technologies that did not exist when this telescope was conceived. And when it was agreed that we would do this, the technology still did not exist. So, you know, we have done what I have always said about NASA. We told people what we were going to do. We made a commitment of a schedule and time, and we have been on that for about 6 years now. So I think the story we have to tell, the record of performance that we have should stand us in good stead. But I think anybody would be crazy to tell you that anything, you know, survives over a transition. But I'm comfortable, as I am about most of what NASA is doing today, that we've got a good story to tell and a record of performance.
Take a few more. Tarek?
Thank you very much. Tarek Malik with Space.com. Dr. Mather, you mentioned that you're kind of, you know, your baby is built. Now it's time to test it. It's got a very intricate deployment sequence. It seems like a lot of things have to go right, a lot of moving parts. I'm just wondering if there's any trepidation on the team of how that's been. I mean, it's been years of testing all those individual things, but it all has to work at once when it gets up there. Thanks.
I think I'd be crazy to tell you I wasn't a little nervous. But I would say also we have a process which does as well as humanly possible to make sure it will do what we said it will do. We are recording everything that we do during the tests. It's a little like packing up your parachute just before you jump. You have to do it the same way that you tested already. So we've got everything is being documented, and the people that will do it are the same people that did it before. So everything you could do to get it right, we're doing that. And I'm not aware of anything that we should do that we're not doing. So I can sleep at night.
Frank?
Frank Mooring with Aviation Week for Dr. Mather. If I'm not mistaken, this will be operational at the same time as the Hubble. Are there particular observations that would lend themselves to having the two space telescopes working, and then beyond that, some of the big telescopes coming along on the Earth?
Okay, good question. There are a couple of things that are kind of obvious. One is that there are things out there that fluctuate. Galactic nuclei have pulses coming out. Things flare and jump, so it's good to get them all at the same time with all the equipment you've got. And just this week it was pointed out that Hubble and Webb can look at the same planets from different angles. Kind of gives you a stereoscopic viewpoint that I hadn't appreciated. They're a million miles apart, so your two eyes are separated by a million miles. So you should be able to see a nice perspective on the planets. I think that's really cool.
Another question over here.
Yeah, Scott Johnson with Spaceflight Insider. I know Hubble is in low Earth orbit. I believe this telescope is going to be placed in a much different place out in space, L2. Can you just speak to that, how that works, how we're going to get it there, that sort of thing?
Okay, sure. We're putting it a million miles from Earth, and it'll be overhead at midnight. So sun, Earth, and telescope in a row. We orbit around that spot because we actually don't want to be in the shadow of the Earth. We need solar power. And we're putting it there because it's the first and only place that is easy to protect the telescope from the sun and the Earth at the same time. Telescope's got to be cold. At that location, you can put up your one-sided umbrella and you'll be cold. So that's the point of going there.
Okay, there's
So
another
it's hard to get there, but not so hard. We know how to do that.
He's headed
Yeah, we'll work on
all the way in the back.
Ken Kramer, Universe Today, Northeast Astronomy Forum. For John, can you talk a little bit about how this telescope will look for the molecules related to the origin of life in planetary atmospheres and the priority that will get, and looking at Proxima Centauri that you mentioned? Thanks.
Okay, well, everybody knows we want to do this. What we have to demonstrate after launch is that we really can. So this subject came up after we designed the telescope. So there's no requirement we can possibly verify on the ground that proves we can. But on the other hand, everybody's completely optimistic that we will be able. So just to remind people, what we do is we spread out the light of a star into a rainbow, a spectrum, and we look for the different wavelengths where the atoms and molecules of a planet would intercept some of the light, and so we'd be able to detect it that way. So there are a few that we should be able to see for sure. Water vapor is one of our top targets. We'd like to know if a planet out there has enough water to have an ocean. We think we can do that.
Another one in the room, and then we'll go to a couple questions online.
Following up on that, Gabe Hopkin, I'm a freelancer. Do you need the planet to pass in front of its star for Webb to get any information, or can you look at planets that don't transit as well?
Both kinds we can do. But the little ones that go in front of the star, that's sometimes the only way we can see them. If they're bigger and brighter like Jupiter and they're far enough from the star, we actually see them as a little dot that's separate from the star, and then we can study them much better. But it only works for big bright ones.
Okay, we'll take a couple questions from online.
Okay, so these are coming in through the hashtag #AskNASA, and German JMC wants to know, what's the probability that space debris will hit the mirrors?
Oh, 100%. and we're designed to handle that. We don't mind if there are little holes in the mirrors. And we have designed to account for everything else that might happen too.
Okay, and we have a second question from Morris Tech in New Jersey. An entire school is watching us. They want to know if they will be able to see what the telescope sees as it happens live, or just as the pictures are released.
And nobody can see it live because they don't come back right away. So we accumulate the data on board and we send them back twice a day to a ground station, and then it has to go processed through a computer before we can all see it. So some of the data will become public immediately, and some of it we'll have to chew on it for a while before it's ready. But it will all become public.
One more?
We have one more. Coming in through Ask NASA, Ms. BD wants to know, will this be as revolutionary as Galileo's telescope?
That's a hard one.
Throwing down the gauntlet.
So Galileo's telescope changed everything for all of humanity. And I think you can't claim to be the first anymore. But we certainly expect wonderful surprises.
Thank you. Perhaps another question in the room, and then we'll look at wrapping up. Here we go.
Keith Cowling, NASAWatch.com. On the issue of going possibly back to visit this, does the telescope have a grappling fixture? I know that was a big dispute for a long time, whether or not there would even be one on there. Is there a grappling fixture on the telescope?
No.
There's not?
No.
Okay.
But we do know how to attach anyway. We can use the ring that we already attached to the launch vehicle with. So we know how to do the attachment if we need it.
So you could go out and attach?
Yeah, but we are not planning on it. We're planning to not need it. Thank you much.
Okay, another question over here.
Hi, Doyle Rice from USA Today. What's the lifespan of this telescope? How long do you think it's going to be up there?
We promised 5 years of science operations. We're carrying fuel for 10. And if we're lucky, it'll last longer. So that's a long time, but it's not infinity. And we'll run out at a certain day.
We have another question here.
I want to ask about the deployment process again. Oh, Lauren Gresh with The Verge. And when going to take? How many steps are involved? And when do you sigh a relief that it's there, it's deployed, ready to go?
I think we're never completely relieved that it's safe, because nothing's ever totally safe. We have about 2 weeks to get the whole thing unfolded. So the first thing comes out of the solar panels and the telemetry dish, and then we wait a little while until water vapor has come out of the carbon fiber stuff, and then we unfold the sun shield. And then that takes quite a while, because we're careful. We go step by step until it's all, we have to be really careful, because there's no way to back up on that thing. You have to just make sure everything's worked step by step. Then we wait a while until it's cold, and then we can start to focus it. So it takes a couple of months before it's really cold. And then we get into the details of does every single part do what it's supposed to do, and how do we optimize the control. So 6 months after launch, we should be ready to do science operations, and you should get pretty pictures. And science.
There's a question back here, back.
Hi, this is Andrea Bartholomew, German press agency. I was wondering if this works with infrared. Will we be able to see these amazing photos that Hubble sent us?
Yes. Yeah. We also do see the same wavelengths that Hubble can see. We don't see the ultraviolet light, but we can see everything from red wavelengths to longer, and it's gorgeous to look at that too. It will be pretty.
Another question right there.
This question's for Commissioner Bolden. This is Scott Dance from the Baltimore Sun. Just curious if, as Senator Mikulski prepares to step down, if you've had any conversations with her, you know, just to reassure her, like you were saying before, that you're going to keep your promises.
All the time. She is still Senator Mikulski representing the state of Maryland, and still the ranking member of the Appropriations Committee all the time. and my guess is, when I am no longer the NASA administrator after the Obama administration, and she is no longer the active Senator Barbara Mikulski, she has my number, and she will probably still be calling and saying, what are those guys doing, or why didn't this happen, or something else. So she will, my hope is that she will remain active and involved in the life of Goddard and the science community of NASA. She has been an incredible advocate. I just don't want it to go by without, you need champions. And she has been a true champion for science, NASA, and Goddard, and in that order.
We have time for 2 more questions, and then we'll wrap up. So who hasn't gotten a chance to ask? Any remaining questions? You've already asked a question. Anyone who hasn't asked a question? There in the back. Nancy, right behind you.
Hi, Summer Ash for Slate Magazine. I was just curious about the deployment of Webb. Prior to Webb, what was the most complicated automated deployment that NASA or any other space agency has done?
To tell you the truth, I don't know, because it was for some other government agency.
Yeah. Chris says curiosity. If some of you remember, just everything had to work, and everything had to work in specific order. And it's like John said, you never stop holding your breath. We never stop holding our breath, even now. Yeah. This is 6 months of terror.
Bated breath.
But there's a limited degree that you can survive for 6 months. So we have to make sure that we don't need to be terrified by doing our job now.
Who gets first? Who gets first dibs?
It's to be,
Science-wise.
yes. The people that have been building the instruments and some other scientists were chosen by headquarters to get first dibs on some parts. We're also going to have a community effort where the entire world can say, this is what we think we should have observed right away, and that data will become public immediately. So those are the 2 things we got set up so far. We haven't chosen yet.
Okay, great. Thank you all for joining us this morning for this special look at the James Webb Space Telescope, which will tell us new secrets about the universe, about our solar system, formation of stars and galaxies, and other solar systems and beyond. As we launch the telescope, I'm sure it will reveal questions we haven't even thought to ask, and the answers to those. Of course, you'll always be able to find the latest information about all of it online at nasa.gov and nasa.gov/web. Thank you for joining us today.